So we're now going to think about another type of partitioning clustering method called model-based clustering. So it's very similar to k-means in that for each observation we want to assign it to one of k clusters. But in k-means clustering we didn't assume a distribution for each data point. We just assigned it to the cluster for which the mean of that cluster was closest. So in model-based clustering, we're going to instead assume a probability density function for each cluster. So we're going to assume that all the observations in cluster J have density f of x with some parameter theta j. We're going to allow these different parameters theta to vary between the clusters. And so what we're going to want to do is we're going to want to estimate the cluster parameters theta 1 up to theta k, and the encoder delta. So how do we do this? Well, we've seen previously that a common way of estimating parameters is via maximum likelihood estimation. So if we think about the likelihood of the parameters theta 1 to theta k and delta. Okay, so let's suppose we're given the parameters theta 1 up to theta k, and we're given the encoder delta. Well, what's that likelihood of the data x? Well, this is the product from all those x's that are in cluster 1, f of x given theta 1, times by dot 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 up to, let's say, all those x's in cluster k, f of x given theta k. Or another way of writing this is we could write it as the product of f of xi given theta 1, where we got all those i's such that delta I equals 1, times by dot 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 the product of all those i's such that delta I equals k of f of xi given theta k. So that's the likelihood. And so one final way of writing this, we could just simply write this as the product of xi's, and the parameter for xi is going to be given by delta I, the encoder. Okay, tells you which cluster we're in. So this is just the product from I equals 1 up to n. So this is the likelihood of the parameters theta 1 up to theta k and delta given the data. So let's say we can estimate the parameters using their likelihood, the maximum likelihood values. So in other words, we let theta 1 hat up to theta k hat delta hat be the values that maximize the values of theta 1 to theta k delta, which maximize the likelihood. Now in this module we're not going to talk too much about how this is done. Okay, it's beyond the scope of the module, but if you're doing the computational statistics module and you've seen the EN algorithm, the expectation maximization algorithm, that's what underlies model-based clustering. One thing we're going to want to note is that the encoder, the maximum likelihood encoder, turns out to be the value of k that just maximizes the likelihood f of xi given theta hat k. Okay. Which is what we'd expect, right? We assign point I to the cluster for which it has largest likelihood. Okay, so that's kind of obvious, but there's a proof of it in the notes you can read through. Okay, but it's kind of obvious why that should be the case. So the most common choice for the deltas, the f's, the densities f, is multivariate Gaussian. So we let f of x beta be the PDF of a normal distribution, what is in p dimensions, if x is p-dimensional, with some mean mu and variance sigma. Okay, so our theta j's, our parameters here, are some mean vector and some covariance matrix j. So just like in k-means, we have this iterative approach for estimating the clusters and the parameters. So in k-means, the parameters were just the mean of each cluster. Here we've got two parameters, we've got a mean and a variance. So our algorithm, and again the details aren't particularly important here, we're not going to implement this ourselves, but the algorithm works by, first of all, we estimate theta j given a value of delta. So this is for j equals 1 up to k. Okay. And then we estimate delta given theta j. Yep. And we iterate as before. So we iterate until convergence. So how this works in practice is we start by picking an initial value of the encoder, delta, and then given that, we estimate parameters, theta. Okay. So if we've got a multivariate Gaussian clusters, we know how to do that. You know, if we've got all the points assigned to that cluster, we use the sample mean and the sample covariance. Then given those parameters, we re-estimate delta using the rule here. We assign each point to the cluster which maximizes its likelihood. Then we go around again. You know, given delta, we estimate theta. Given theta, we estimate delta, and we keep doing that until convergence. Okay, and we can do this formally. We can make sense of this algorithm formally. It's called the expectation maximization algorithm, the EM algorithm. But as I say, it's a bit beyond the scope here of what we're doing. I just want to briefly pull out the link between this model-based clustering with Gaussian clusters and k-means clustering. So let's consider the case where, let's suppose we're going to fix sigma 1 up to sigma k to be just some multiple of the identity matrix. Yep, so all the clusters are going to have the same variance. Well, what's our maximum likelihood rule then? Well, it is given the cluster means mu1 up to mu k hat, our encoder is the value that maximizes, with respect to k, the density of xi given mu k and sigma I. Well, what is that? Well, that is essentially the same as that is the same as the argument that maximizes. If we write in the density here, well, we don't need to bother about the variance term at the front because it's all the same. So this is going to be the same as the value of k that maximizes the difference between xi and mu k squared. Yeah, if you think about what the Gaussian probability density function is. And we can see here that this is the same as the value that minimizes with respect to k the distance between xi and mu k. I've got some hats here, didn't I? Okay, so what is this? Well, you can see this is exactly the same as k-means clustering. So in this case, model-based clustering is the same as k-means clustering. And so this gives us a way to understand what k-means clustering is doing. We can think about k-means clustering as doing model-based clustering, but where all our covariance matrices are the same and they're all equal to the identity. Okay. Now, that may or may not be realistic. Okay, but that's kind of the idea behind k-means. Model-based clustering allows us to have covariance matrices that aren't diagonal. It allows us to scale the different variables. It allows us to have different covariance matrices for different clusters and so on. So model-based clustering with Gaussian clusters is much more powerful, but we have more parameters to estimate, and that leads problems with identifiability and so on. Okay, so let's see an example. So let's have an example. Let's look at the iris data again. Now, as I said, the implementation details of model-based clustering are beyond the scope of this module, but we can use an R package to do this very simply. Okay, so there's this mclust R package, and within that there's a command mclust, and all we have to do is pass in our data set. So I'm using this iris2 data set I defined before. So that, remember, that was just the 4 numerical columns. So the sepal length and width, the petal length and width. And then we just have to specify the number of groups, which is G here for this package. And it fits the clusters, it fits the parameters, and it gives us back a clustering. So this is most useful in terms of the plots. So if you plot the output here, you have to specify what type of plot. And the 2 I think are most useful are the classification plot. So what it's done here is given a scatter plot of the data for each pair of the original covariates. Then it's coloured the points by what cluster they get classified to. So you can see here, if we look at, say, this top right plot, so that's the sepal length against the petal width. As you can see, you've got 3 clusters, which we specified ourselves, G equals 3. And then you can see which point gets classified to which cluster by the colour. You can also the cluster mean and this projections in 2 dimensions, and the cluster covariance as well. You can see the same for the other variables. So the plots and the upper diagonals are just a copy of the plots in the lower diagonals. So you need to look at one. Another sometimes useful plot is to do the density plot, and you can see here that we've got the density of each of the 3 clusters plotted. So in some cases they overlap quite significantly, so you can only really see 2 here, but there's 3 clusters and you can see the densities given. So we've not looked in great depth at model-based clustering, with a very light coverage of it. There's a lot we could say and do, but it gets very complicated, and it's going to be a bit beyond the scope here. In particular, things like how we choose K, the number of clusters, would require us to develop a lot of theory. So we're not going to do that here. I just wanted to present this as a way of doing clustering that assumes a probability model for the underlying data.